Good morning. I'm chair for this morning session. Let me start today's talk. First speaker is Nina Amini, the series of lectures. So please start.
Thank you very much, and hi everyone. So today I will continue. This is somehow more technical talk. It's about beyond discrete time, and also I will talk about our recent work regarding discrete time, but not QND measurement. So first of all, I will treat the case discrete time and continuous time and QND measurement, and then I will go how we can to go beyond the QND. Okay. So this is the first part of the talk. So first of all, I will describe how you can study the stochastic behavior of a diffusion process in classical case, just to give you some tools. Because we want to study the stabilization problem for a continuous time system, so you need to know what are the elementary tools. So you need, for example, consider XTZ, so which is a diffusion process, so which is defined in some metric X, and suppose that your initial is Z. And in fact, when you study asymptotic behavior of a dynamical system, you study the equilibrium of your dynamics. And you want to see what are the behaviors, for example, do you have a stability in probability, or globality stability, or exponential stability, and so on. So what is stability in probability? In fact, if you can say that the limit of the probability when your Z converging to Z tilde, to the equilibrium of the supremum of the norm between XTZ and Z tilde, if you can say that this probability is greater than epsilon is equal to 0 for any epsilon positive, so then you have a stability in probability. And you can say that you have a global stability if you have a stability in probability, and moreover you have also the probability to have the limit of XTZ equal to the equilibrium is equal to 1. Okay. So these are some definitions. And then if you remember yesterday I talked about the Lyapunov function. So if you remember, let me just write this before. If you remember, there was a theorem said which if you have a Lyapunov in discrete time, if you have the expectation of your Lyapunov at xk plus 1 knowing xk minus v of xk, if this is equal to 0, so then you can say qxk with qxk, which is a positive function. So then you can say that x infinity is included in the set E such that q of x equal to 0, right? So now we want to define the analog of this, the increment of the conditional expectation in continuous time. So here you have, instead of the increment, you need to work with the infinitesimal generator. So in fact, you have a stochastic dynamics like this, so bxt dt plus some diffusive term here, sigma xt dwt. And L, in fact, the operator L corresponds to the derivation of the expectation of, for example, this is the operator, so then you need to apply it to some function vxt. So d of dt of the expectation of vxt is equal to lvt. Okay, you apply your L on vt. And this is given by the changes in the expectation of vx. It's very similar to discrete time, right? And here you need to use the Ito formula. So because I don't know if you are familiar with the Ito, otherwise I can write. It's fine. I can continue. So you have the infinitesimal, so which is the derivative of v with respect to x, and here you take the deterministic term dx plus the second derivative, half of the second derivative times sigma x square. And in fact, if you know that this is a negative function, so then you have the stability. And by the Kushner's theorem, you can say that you have the convergence in probability towards the invariant set, which is included in LV0. It's exactly similar to this right here. So now, so today, when I talk about continuous time, so for just simplicity, I only consider the case of spin-half system. And because for for example, n-level system, you have, there are more technical things to do, but the idea remains almost the same. In fact, you have the state space, so which is 2 times 2 density matrices, so which is positive, Hermitian, and trace 1. And your control, in fact, is appearing in the Hamiltonian. So you have UT here. We suppose that you have sigma y as Hamiltonian, and you measure sigma z. Okay, your measurement operator is sigma z. And if you look at the equilibria of this equation, so you have 2 equilibria, so which is rho g, you're in the state and excited state. And the problem is to stabilize deterministically one of these states. Okay. So you can, for example, you suppose that you want to stabilize rho e. You consider the distance function like this: 1 minus trace rho t rho e square. And if you write LV by using the formula I gave you, so it's you have this expression, and you want to have for stability. We said we need to do LV as the negative function. So then the natural choice for your feedback is like this, right? You take minus of this because this term is negative, and to make the first term negative, so it's sufficient to take UT, which is minus this value. So it's just to give you some references in this regard. So the first treatment was in 2005. So in the group of Mawuchi, 100, and Stockton. So they studied the spin-half system also, and they proposed the feedback and a Lyapunov function. In fact, you can say so. This is somehow the inverse. First, they guessed the feedback that can stabilize one of the equilibria, and then they said that what is the Lyapunov function which corresponds to the control. But in somehow they use the control theory, but some part remained to be treated later. So in this paper, so then Miraimi and 100, so they proposed feedback and a stabilization of n-level system, and also they mathematically they proved the stabilization. And later in this paper, so in fact in this paper, the authors they proposed a switching feedback. Okay, if you remember my talk yesterday, so there was a switch feedback. So I have some part when we are very close to the target, and the other part when we are close to the bad attractors. So this comes exactly from this paper. So in continuous time. So but later this is improved in this paper. So the author proposed a continuous feedback without switching. He showed that you can stabilize an n-level system. In fact, you have so this is the first paper that I took. So you have the spin system here, so which are in interaction with the optical modes, and then your feedback, in fact, is the magnetic field, which is applied in order to stabilize. Here we want to stabilize. If you write the density matrix in the Bloch sphere, so you have you want to stabilize one of the poles, so which is x here is 0, 1, and so this is a natural feedback because it is, if you check, is 0 at the target, because you don't want to apply any control when your dynamical achieved at a target state 0, 1, and then they numerically find this Lyapunov function. So here is the feedback that the authors in 2007 they proposed. So the first term, it comes. If I go back in this page, so you have ut, so which is minus of this. So in order to make this term negative, so then you say that when we are close to the target, but in some sense, you have, if you apply this feedback, you can stabilize. And if you are not very close, so it's less than gamma over 2, the trace between rho t and rho e, so then you apply a constant feedback, so which is here is 1. And you can say, how about when the trace is between these two values, what you can do? So then they show that if you take ut as this, if the last entry of rho t into this set is comes from this value, then you take this. If otherwise, you take a 1. Okay, so it depends the last entry of your trajectory into this set. So then there exists, they show that then there exists gamma such that ut can globally stabilize the system around the target state rho t. So in fact, you have the expectation of rho t which converges to rho e when t is converging to infinity. So just to give you the steps that they did. So in fact, they choose such a Lyapunov function, so which is the distance between your density matrix rho and rho e. So this is very natural, and they take some alpha and define some set in order to study how much the trajectories they are close to the target or not. So then they define this set as greater than alpha, and so on. Okay, and the other possibilities. So in step 1, they say that if the initial state is in the set S1, so this is the worst case, right? S1, because rho is orthogonal to rho e. So then the constant control U1 can ensure the exit of trajectory in expectation from S1. And the second step, they show that there exists a gamma such that whenever the initial state is inside the S greater than 1 minus gamma, and the control field is to be U1, then, so suppose that you are not 1, but you are still close to the bad attractor. So then with taking this control, you can show that the expectation value of the first exit time from this set is a finite value, okay? So in the first step, just to summarize, so when you are at S1, so if you look at the sphere, so you have, so this is S1. So you said the control 1 can make the trajectory exiting from the S1, and if you are, for example, is 1 minus gamma, if the trajectory is here, so then you can say that the control can make the trajectory exiting from this set with a finite with the expectation time which is a finite value. So now you suppose that you are inside the 1 minus gamma, and then you take this control. So then you can, they show that the path so never exit the set 1 minus gamma over 2. Okay. So if you look at 1 minus gamma here, so then you can say another sphere 1 minus gamma over 2. So then they show that they never the trajectory can exit this sphere 1 minus gamma over 2. Okay? With larger with a probability which is uniformly larger than a strictly positive value. So then once the trajectories are blocked in this sphere, so then you can show that the convergence to the equilibrium. And the final step is to show that because you take the different not continuous control, right? So you have ut1 and this value. So you need to show that if you consider a PS a different control depending on the behavior of your trajectories, so then the solution is unique. Okay? So that's the final thing that they did. So then, like this, they showed very properly, so you have the global stabilization towards your target. And the other paper that I took is improve this the form of the feedback. So in fact, this in order the switching, so you have the continuous feedback. So you have this term plus beta 1 minus trace. So this term, in fact, is active when the trajectories is dominating, when the trajectories are very close to the target. And this term, in fact, is active, is dominating the whole if you are far from the target. And then you have the stabilization if you choose your parameters properly, okay? And the ideas of the proof, first of all, so they show that the state rho E is stable in probability. And then, so the other is quite similar, the steps. So there exists gamma, almost all sample paths, which never leave the set 1 minus gamma. So they will converge to rho E. So however, here we don't have to look at, for example, between 1 minus gamma over 2 and 1 minus gamma. So the proof is quite simpler. And for almost all sample paths, there exists a finite time. And after it, they never leave this set, which is S less than 1 minus gamma. Here? Alpha is here, beta is this value, and eta is the efficiency of the. Yes. So now I want to talk about our work in this regard. So we improve the convergence speed. So we prove an exponential stabilization. And the whole idea is to consider a good Lyapunov function, and then the proof was quite technical also. So, but I choose to present a spin half because it's easier. So in fact, just to give you in classical stochastic theories in stochastic control, for example, how the people they look at exponential stabilization. So I will define what I mean by exponential stabilization. So usually you need a distance right between your current state and your target. So then that's why I take the burst distance here. I define between two different states. You can define the burst distance like this. And if you look at the two-dimensional state space, so then this expression is simplified. You have this this expression, and so now I mean in fact you can define the distance between two states or between one state and a set of states. Okay. So here, how you can define this? So E here is a subset of S2, and you take just the minimum of the distance between your row A and any row which is included in the set E. Okay. And here I define just the neighborhood around the set E. So you take all the rows such that dB row E is less than R. So then so this is just the bool, so which is with a real R around E. So now I will define some stability. So in probability, exponentially stable in mean, and almost surely exponentially stable. So you have some dynamical system like this, and you have some equilibrium row bar. So you can talk about stability in probability if you can say that for every epsilon that you choose here, and any R that you take around your target row bar, if the probability to have rho T inside the BR row bar for any T greater than T0 greater than 1 minus epsilon, so then you have stability in probability. However, you have exponential stability in mean if you can say that the expectation of the burst distance between rho T and rho bar is less than alpha and the distance, in fact, you start at some rho t0. If initially you are close to rho bar, and also you can say that the expectation is less than this term times the exponential of minus beta t minus t0, so then you have exponential stability in mean. So this is for any rho t0 that you take in S2. And you have also almost surely exponential stability if you have the limit of supremum of 1 over t. The log of the distance between rho t rho bar is strictly negative, almost surely. So then you have almost surely exponential stability. So here I will focus in this type of exponential stability. So this is just give you the recall about the dv, how you can use the A2. So you have dv, which is LV plus the expectation of v with respect to rho, and here gndw, so which is the term, diffusive term here, right? So here, so this is our system, so which is 2 spin half. So you have in the Bloch sphere, you have this presentation, and so this is the neighborhood. So this is a Bloch sphere size. So you have these constraints on x, y, z, and you want these are the two equilibria. So if you write this in the coordinate x, y, z, so it's 0, 0, 1 and 0, 0, minus 1. So this is our system. So you have some physical parameters. So here, so which is the difference between the frequency of E and G, and M is the strength interaction between light and the atoms, and U here is the control, and eta is the detection efficiency. So here we consider also imperfect measurement. So if you look at if you write the equation in the Bloch sphere, so you have x, y, z like this, and the control is appearing in x and z. Okay, so in y coordinate there is no control, and you can see in somehow your x and z, so they are coupled here, right? So that they have correlation between them, and between y and z and so on. So here I will talk about support theorem, so which is that I will use later. In fact, for a stochastic system, so this you can if you consider your stochastic system like this, if you look at the deterministic control equation, so what is the mean? In fact, so this is a Stratonovich form of this equation, so which is a deterministic, and you replace Brownian motion by a piecewise constant function u, and you want to study, in fact, how the trajectories they behave, okay, by looking the deterministic equation. So I want to briefly describe, but this is really a domain. There are many research regarding the support theorem. So you have, in fact, if you define the gamma x, so which is the solution of this, so xu for any u, which is a piecewise constant function. So then you can show that the set gamma x, which is defined here, corresponds to the smallest cross set of the continuous trajectories starting at x. In fact, you can say that the probability to so the probability to have omega inside omega, so such that x omega is belonging to this set is 1. Okay. So in fact, this set can give you the solution of your stochastic system. Okay. So why is useful, especially in control theory? Because by you have you know how instead of working with the stochastic system, you need to consider the deterministic system, the Stratonovich form, and then you can, for example, study the controllability of your system. If you start in some initial state, there is any positive probability to achieve at around your target state in a finite time or not. So it's sufficient just to consider the deterministic system, and you find only one trajectory that can go over there. So then you can say the probability is positive. So in fact, you need just to construct the piecewise constant function here. That's the thing that we use in order to show the controllability of the target. And here there is some other lemma. So this is I don't want to enter to the proof or detail, just to say you that we need also some conditions on the control in our stabilization. So if just quickly talk about this lemma. So if you consider the evolution without feedback, if you have an equilibrium or rho E and rho G, and you can show that if initially the state is not inside the E2 bar, so then for any t greater than t0, the probability that rho t is not inside is 1. Okay? And also with feedback, you can show the similar result. However, you need some constraints on your feedback, so which is like this. So just for now, you need to know that the feedback should satisfy this condition for some technical issues. And here, so here for the stabilization problem, you need to know what is the asymptotic without feedback. So here we will study when the control is 0 and initially the state is inside S2. So then you can show that the set of the equilibria is exponentially stable in mean, and also almost surely. And also we give the rate of convergence, which is eta m over 2. Okay? M, it was the interaction between atom and field, and eta is the detection efficiency. And in order to show this, we take this Lyapunov function, so which is the square root of 1 minus trace square. And you need to look at the infinitesimal generator of V. It can be shown that this is given by something minus eta m over 2 V rho. And if you have, in fact, for the exponential stability in mean, if you have LV, which is minus some constant V, so then you have exponential VT, because here you can use the Ito. The expectation of this is V rho 0 plus the integral of LV, and here LV is minus CV, which is minus eta m over 2. And now you can use the Gromwall lemma, so then you have expectation of V rho t. So which is, so here you have expectation, so which is less than V rho 0 exponential minus eta m over 2. T minus T0, I take but okay. Okay, so this is so this is equal. Sorry, this is not because I have this is equality, right? So now, so why you need to show that this is a good choice. This Lyapunov is a good choice for the distance. So you need to relate your Lyapunov to the distance, to the Bourse distance here. So in fact, you can show that V is between this distance with some constant C1, C2. And then you can say the similar thing for the expectation of the distance. And once you have this, so then you can say that the lim sup of 1 over T log of dB is less than minus eta m over 2, almost surely. So this is the definition of the exponential stability in almost surely, right? And in order to find the probability, so the trick is like yesterday. So in fact, you know that the population is martingale because L is 0. So then you can determine the probability like easily like that. So for the numerical simulation, so we used, in fact, you have this equation. So you need to discretize this with md so this is a jump operator, so which is identity minus this dt plus some dy. If you use the Ito formula, you can show that this cross map corresponds to this equation. And here is our simulation. So you have, you can see V rho converges to 0. exponentially because this is our reference to study the exponential rate. So you can see the black curve, so which corresponds to the mean value of the trajectory is below this reference. Okay, so you have the exponential convergence. So now we wanted to obtain some constraints on your Lyapunov in order to say that once we have these conditions, so then you can say exponential convergence. So in this theorem, so we show that suppose that your U is chosen well, so with lemma that I take, so it satisfies some constraint. And suppose that your V is continuous inside S2, and also it's twice continuously differentiable on the set S2 minus the set of the equilibria. And also if you can bound your V with a distance like this, and if you have LV which is less than minus CV for any R, so which is between 0 and square root of 2, and for any rho which belongs to this set minus the target, the equilibria, so then you can say minus the target, then you can show that rho bar is almost surely exponentially stable. So to do this, in fact, the proof is it contains 3 steps. So first of all, we show that rho bar is stable in probability. And then in step 2, we show that for almost all sample packs, there exists T such that for any T greater than capital T, so rho T belongs to this set. In order to show this, in fact, we use the support theorem. And finally, step 3, we say that rho bar is almost surely exponentially stable. If you are interested, you can see the details of the proof. So now I will introduce you some other works that we studied. So we proved the exponential stabilization for n-level systems. And in this paper, we wanted to consider the imperfections and also the case that you don't know the initial state. Because if you don't know the initial state, maybe I can come back. So you have some d rho, so which is a f rho u, and your d y is dw plus something trace L plus L dag rho dt. So suppose that you don't know the initial state, so then you take an estimation rho hat, and you write d rho hat, so which is f rho hat dt. And in fact, dw here is you can write it as dy minus trace. Okay. So d rho hat is f rho hat dt plus g rho, so dy minus trace. So here rho hat, and in fact dy depends on the true state, so which is dw plus trace L plus L dagger rho dt. If you replace this here, so you have an extra term in dt, so which is the difference between trace of L plus L dagger rho minus trace of L plus L dagger rho hat dt. And in fact, the final equation is f rho hat dt plus, so this is rho hat, g rho hat dw plus some extra term, so which is trace L plus L dagger rho minus trace L plus L dagger rho hat dt. So in fact, you can see that you have some coupled equation between rho and rho hat. So here in the second paper, so we study how you can study the stabilization of the coupled system. And it was quite technical. And here we show that you can you can also use these techniques in order to exponentially stabilize the untangled state, like GH state. And later, so we wanted to improve our feedback, because the measurement-based feedback, it takes time to be implemented. So how you can reduce the dimension of the density matrix? In fact, you want to use the less information of your state in your feedback design. So here we show that it's sufficient to in fact, this is proposed by Pierre Bichon. Numerically, it was tested by him. And here we provide the proof for that if you take only the diagonal elements of your density matrix in your feedback design, so then you can ensure the stabilization once again. And in this paper, in fact, we look at some projection filter. In fact, projection filter approach. So in fact, you have the space of the density matrices. So you want to project the density matrix. So this is, first of all, I think it was looked at by Mabuchi's group and Van Handel. So then you project the tangent space of the density matrix to the tangent space of a manifold with a less dimension. And here we provided the projection filter approach, and also we show that if your feedback depends on this projection filter, you can still ensure the stabilization. If you don't have questions regarding this part for continuous time, I can go. So up to here, I suppose that the measurement is QND, so which means that it's the diagonal. But now I want to talk about discrete time, but not necessarily QND measurement. Okay. So this is quite new. Is that there's no? I'm not aware of any other work in this regard for the feedback and stabilization, and even for selection. So I will talk about this if you don't have a question. So in fact, so this is the space of density matrices. So here how we can modelize this problem. In fact, for the QND measurement, I said the cross map are diagonal elements. But here you will see the cross map, in fact, is not diagonal, but it's a block diagonal. In order to show this, you need some structure for the Hilbert space. That is why the people, so there are some works in this regard. So you need to look at the quantum channel, so which is the sum of the VIX, VI DAG, such that so these are the cross, so it satisfies the identity. And here you can relate the expectation of rho n plus 1 knowing rho n. You have a Markov chain like this. And the probability to have E is given by the trace. And here is our channel, so which is the sum of VI rho, VI DAG. You can show that the expectation of rho n plus 1 knowing rho n is given by the phi of rho n. In fact, quantum channel, in some sense, is inspired from the transition probability in classical probability case. So just to formalize mathematically what is a QND. So for a QND case, you have some bases alpha alpha, so which are the fixed point of this. So these are called the pointer state. For example, for the LKB photon wires, NN, it was a pointer state. And there was in these two papers that I talked yesterday. So we have you can show that if you have some identifiability. So the probability of I knowing alpha different to probability of I knowing beta, then you can say that there exists a random variable gamma, so which is among pointer states, such that the limit is given by gamma. And you can also determine the probability to have alpha, so which is the trace of alpha rho 0. So this is for QND. So now we want to provide a similar result, but in not the QND case. So that is why we are working with the set of the invariant state space. So which is the intersection between your density matrices S and all of the fixed points of your canal, so which is phi x equal to x. And you can decompose, in fact, CD into recurrent subspace and transient subspace. So this is similar to the Markov chain. So there are some set recurrent, so which is the space that the Markov chain they will come back with probability 1 in later time. But the transient subspace is a subspace that so there's a positive probability that they never come back. So then, in fact, the recurrent subspace is the supremum of the support of rho, knowing that rho is inside the set D, so which is the set of the invariant space, and the transient subspace is the orthogonal of the recurrent. Okay? Just so briefly about this. So there is a very nice paper of Baumgartner and Narnhofer in 2012. So they show that you can write the recurrent subspace as the direct sum of the HU. So which is what are HU? In fact, they correspond to the support of an extreme invariant state rho infinity. In fact, rho infinity. What is rho infinity? So the set of we said D is S intersection with the set X, such that phi of X equal to X. So in fact, the rho infinity U, it corresponds to the extreme invariant state. What does it mean by extreme? In fact, you can show that the set of invariant states here, they construct a convex set, and you take just the extreme points of this set, and you call this the extreme invariant states. Okay. So and HU here corresponds to the support of an extreme invariant state, and you can show that in fact HU it corresponds to the minimal enclosure. What is the enclosure? In fact, if you have rho which is in S, so then you have phi of rho which is in the. So then you can phi rho which is sorry. So HU, for example, is an enclosure. If rho is in HU, so the support of rho. So then you have the support of phi rho, which is included also in HU. And this is minimal, which means that you cannot find any other set which is included in this set with this property. Okay. So in this paper, the author they show that you can write the recurrent subspace as a direct sum of a minimal enclosure. And this decomposition, in fact, is not necessarily unique. And for the case of a QND case, in fact, you have your Hilbert space that can be written as the sum of direct sum of the one dimensional. Okay, so which is C E alpha, and E alpha corresponds to the pointer state. So you can see what is our difference, that the mathematically of the structure of the Hilbert space, that with respect to QND case, instead of the one dimensional, you can have here the subspaces which are more than one dimensional, and you want to study the stabilization of the states which are supported by this minimal enclosure HU. Okay? That is our goal. And if you do if you use the result in the literature, you can show that. So for VI's on the QND case, we have the diagonal, but here you can have the diagonal, block diagonal, and some Moser terms here. And but these are 0. So here we suppose that we don't have the transient part. So then your VI has this form. In fact, the block here, they correspond to the elements which are supported by different minimal subspaces H1 and Hn. And here we want to provide a similar of the, if I just go back to QND. So you have, you need this for the selection of the pointer state. So the property of I knowing alpha is different to probability I knowing beta. So now we want to give a similar identifiability hypothesis in order to show that the trajectories, they become supported by one of these minimal invariant subspaces. And to do this, in fact, you need to look at the invariant state of your canal. So which is, suppose that you have different extreme invariant states. And there exists some sequence, I1 to IL, such that the probability to have this sequence, if the trajectories, they are supported by this rho infinity u and not support the trajectories, which in fact have said to the subspace which includes this extreme invariant state, and the subspace which includes this invariant subspace, if these are different, you here, yes. Yeah, it's a good question. In fact, it's not very easy. I mean, so, but this is always. In fact, this is a very. You cannot relax this condition. In fact, you need this. I mean, but this is a. If you do simulation, you can say this is after some sequences you. Yeah, this is I will come back. I will go. I will talk about this. How you can. What is the length, for example, of the sequence that you need? Good question. So in fact, here our aim is to show that under ID, in fact, the quantum trajectories, they become supported by these invariant subspaces. And here we want to check the speed of convergence of this selection. In fact, sorry. So in this paper, so we show that you have the selection, but without the speed of convergence. Okay. And to the proof, we use the martingale properties of the population and the identifiability assumption. But here. We want to show that you can the exponential stabilization in mean, so which means that if you take a Lyapunov function W, so then you can show that the expectation of W rho n is less than C exponential minus gamma n. So this is our Lyapunov function that we propose, so which M alpha, which is the orthogonal projector onto H alpha. And you sum over any alpha different to beta. So the key points here is that, in fact, the ID, the hypothesis ID that I explained for the extreme invariant state, is true for any state which is supported with different minimal invariant subspace. So this is that is why we call this uniform ID, and this is really key to show the exponential. In fact, I don't give the detail about this. So in fact, we show that uniform ID ensures that there exists a length n such that for any rho alpha, so which is supported by H alpha, and rho beta, which is supported by H beta, there exists a word in such that for any n, in fact, such that the probability rho alpha of in is different to probability of rho beta in. And here we look at in order to show the exponential. So instead of for example, here you look at the k plus 1 knowing xk, but here you need to look at the increment of length n. So n is in fact the length of the identifiability that you need to check for your sequence. So here we show that this expectation is less than some kappa W rho k with kappa which is strictly less than 1. Okay. And this is strictly less than 1 because of the identifiability that I said here. Because for any state rho till alpha, so which is supported by H alpha and rho till beta, these two are different. Okay? If you use the Cauchy-Schwarz and so on, so it's and you can see that the equality is happened if identifiability is not verified. So then here we show that uniform ID gives a kappa is less than 1. Okay, so now, so up to here, so we showed that we have the exponential stabilization toward the different subspaces. But how about the feedback stabilization in this case? So we have the random evolution towards one of these. So we apply a control, so which is a unitary, and we want to stabilize, for example, this case. How you choose your control? So in this theorem, so in fact, you want to stabilize the target minimal invariant subspace alpha bar, and it's sufficient to take a Lyapunov function like this, so which is a square root of 1 minus trace of m alpha bar rho plus some epsilon, and the sum of beta different to alpha bar of a square root of trace of m beta rho. Then you can show that if you apply your feedback every n times, which corresponds to the length of the identifiability, and which has this form. So you take the argmin of this z function, and then you apply your control at the intermediary state, so which is intermediate state, so which is just after measurement, and if n is different to this value qn minus 1, so then you can take 0. So your control is active on every n steps. And here we show that you have the exponential stabilization in mean. If you have some controllability assumption, if you remember my talk yesterday, so for Q and D, so we need also a controllability assumptions. It was the Laplacian, it was connected, if you remember. And we wanted if the Laplacian was connected, if the Hamiltonian it was connected, so then you can stabilize your pointer state. And here you need a similar condition for this case. In fact, if the sum of the HHB for any beta different to alpha bar is included in the set in the vector space of HK phi j, and here you need only to look at from K1 to D, and J here it's going from 1 to the dimension of your target subspace alpha bar. If this is included to this, so this ensures that you can go from any subspace to other, so there are some sort of connectivity, and then you can show that the expectation of your Lyapunov is less than this, and in particular this, which gives you the exponential stabilization of the subspace H alpha bar, right? Of the states which are supported by H alpha bar. So in fact, the proof ideas is to do this. In fact, you need to consider different sets. For example, S less than alpha corresponds to the trace of M alpha bar rho less than alpha. And when we are, in fact, if you are far from the target subspace, so you have, in fact, the term V, so which is here square root of 1 minus trace M alpha bar rho. So then this is dominating, and even this term is not exponentially, is not the increments that gives us the exponential, but this term is dominating, and then totally your Z, you have the exponential decay every n steps. And if you are inside these two intersections, so this is the R term, and for us greater than 1 minus delta, so then there's still a R term. So then totally you have, you can show that for each region you have this. In fact, for all of this, the important thing that you have the uniform identifiability. In fact, any state supported by different subspaces are identifiable if you have identifiability only for the extreme invariant state. So in order to conclude, so my talk, in fact, we have shown the exponential stabilization in mean for discrete time quantum trajectories. So in fact, this is so here we consider only the case when we have recurrent subspace, and there is so my colleagues Pellegrini and Benoit and the students, they showed also that the case when you have the transient and also imperfection, if you are interested to look at. And here we have shown also, so this is regarding continuous time. In fact, we have shown the exponential convergence almost surely with QND measurement. So actually, so with my student Nicolas and the others, so we look at the quantum trajectories, the continuous time quantum trajectories, and we want to provide similar results for the continuous time. And this is not trivial because identifiability data set, so you need the length of the sequence. So in continuous time, this is not obvious how to treat, but we have a work in progress. And also the other thing is application, how we can apply this result for example, error correction. And when you want to stabilize subspaces, it's important to protect the space of code from perturbation. So we will see this application. And also we want to find examples for this. Like for example, one of them could be maybe a GKP stage. So where we have a subspace that you want to protect, and so on. Okay, thank you. I don't know. Thank you very much.
Thank you very much for a nice talk. So, do you have questions or comments?
So for the discrete QND measurements, what you showed is that at long times it goes to one of the pointer states with probabilities given by the Born rule, basically, right?
For the QND case?
For the QND case.
Yes.
And then for the non-QND case,
yes,
it goes into this blocks.
Mm-hmm.
But what is known about the probability? I don't know if you mentioned that.
Yeah, the probability is similar to that one also.
It's still no.
It depends also the population of the say the trace. In fact, is Q alpha of 0, so it's the population, which is the trace of M alpha rho 0. I think this is our probability. Okay. Instead of so this is the probability to have to can write so the support of on rho is inside the H alpha. Okay. So you want to this event, for example, A. So the probability of A is given by. Okay. So it depends on the. So M alpha is the orthogonal projector to the H alpha, and you look at just the trace of it.
Questions?
Thanks. So you've been applying the Asymptotic method and other sort of related methods to feedback control. Well, in the QND case also to just projective to a random state. I wonder whether you had any idea, any thoughts on whether you could apply the same methods to the adaptive scheme that I talked about, where you make the system just by using an adaptive measurement, asymptotically only spend time in a finite number of states.
Yeah, exactly. This is also very good direction that I would like to look at also later, because the feedback is difficult also to implement it, especially this form is not very easy because we need to look at the arg mean. So this is not always easy. For example, for the LKB, it was can develop a UU and so on and look at the arg1 minimum, but adaptive measurement and other strategies, Markovian feedback and so on should be interesting.
Mm-hmm.
or even the mean Caesar rules. We have some things to look at here.
Thanks.
Thank you.
Okay, so then answer questions. If not, let's thank speaker.
Thank you very much.
And we have